Bismillahirrahmanirrahim. In the last class, we were talking about the all-pass filter. Before going to the all-pass filter, we have also mentioned that what is group delay, and based on the linearity of the phase response, how the group delay can be changes. It might be a constant value, or it can be varied with respect to the value of the omega. So in case of IIR filter, it makes the life difficult since the phase response of the IIR filter are usually non-linear. So to protect our system from the phase distortion, we must introduce a all-pass filter after an IIR type filter. Always this is mandatory. So we need to introduce a all-pass filter after an IIR filter, so that the combination of these will work as a FIR type filter, which mentioned that the phase response will be linear, and that's why the group delay will be remain constant. Okay, so as we have derived in the last class, for a single order all-pass filter, what we can learn here, we can write it here like this: B plus 1 by Z divided by 1 plus B divided by Z. From there, we can also write this is BG is equals to plus 1 divided by Z plus B, where this represent what the zero location. From there, we can find BZ plus 1 is equals to 0. From there, we can find Z is equals to, we have minus 1 by B. So that is the zero location. On the other hand, from the denominator, we can find Z plus B is equals to 0. From there, we can find Z is equals to minus B. So what we have found that the pole location is at minus B and the zero location is at minus 1 by B. And that is the relation. So if we want to draw it in the Z plane, this is minus B. Let's say this is the location of the minus B, the pole location. Where is the zero location? That is 1 by B, probably there. What could be the value? Let's say it is minus 0.8, minus 0.8, and this is minus 1 divided by 0.8, which is more than 1. So if we have number of poles and zeros like this, if the transfer function is like this, we have B plus Z to the power minus 1, 1, 0, C plus Z to the power minus 1. Then we have the pole locations. We can determine the pole location as 1 plus B Z to the power minus 1 and 1 plus C Z to the power minus 1. So what are the pole location? The pole location would be a minus B and minus C, and the zero location is minus 1 by B minus 1 by C. That is the thing. So again, if I draw it here, all the poles and the zeros are real here. We are just choosing the value real poles. So if we consider this pair, I have already mentioned that this is, let's say, this and these are the pair. For this one, for C and minus C and minus 1 by C, let's say if this is the value of minus C, maybe with the proper scaling, we can find that the zero location is here. So that makes a pair. So it makes one pair, this makes one pair, and this makes another pair. And that's why this is known as the romantic function. That means you have the couple of the poles and the zeros, and they have the relation between poles location and the zero location. And this is for the real pole, that is all the poles are in the real axis. Now if we can find this is the pole location, of course the zero location is there. If this is the pole location, for that one the zero location is there. So these are the real pole. We can also extend our discussion for conventional complex pole as well. So whenever we have the complex pole, so forget about this term. We have z to the power -1 minus ci, or you can say c1. The other one should be 1 minus c1 z to the power -1. Well, we have already learned this thing. Here we are making the conjugate of that. So that is the process for the complex pole. So what does it mean? If we have the ci, that means this one is equals to r e to the power j theta, then the c1 conjugate is equals to r e to the power minus j theta, and 1 divided by c1 star, that means the conjugate of that, it will be 1 divided by r e to the power j theta. So in the z plane, how it looks like, if this is the location of r, the pole location. So how that has been defined, that is this one can be defined as the value magnitude is r, and what is the phase? Phase is e to the power j theta, e to the power j theta, because that is in the Cartesian plane. Have both real part and the imaginary part. And what about the zero location? This is for the pole location. About the zero location, we have 1 divided by r e to the power j theta, and which is the zero location. So how we can draw this? What we can do, we can take a straight line over this. If we have this pole location, 1 divided by r, this is the value, this is 1 divided by r, which give you the zero location, and the phase remain the same for the both the pole and the zero location. Okay, so if we have a pole location over this at this moment, what we can do, we can make a straight line from the center and extend it. I should put the pole locations there, and the zero location is this, where this is the value of, let's say, r1, and this is the value of 1 divided by r1, and the theta value, the angle with respect to the origin or the x-axis, they remain the same. Okay, so in conventional way, so whenever we have the pole in the complex plane, of course we should also have another pole here. So we should have another pole there, and how we can find the zero? Of course, in the similar fashion, we can achieve the zero like this. So whenever if I give you this in some in your exam, let's say this is the zero locations are given, and this is the pole location is given. Now put the other pole and zero location for the all-pass filter. What would be the answer? The answer would be like this. For this zero, for the first zero, there should be another zero here, because that is a complex conjugate. And now the second point, we need to extend this line, and we need to extend this line, because we know that if this is r, another pole is 1 divided by r, so maybe there. And similarly, we have another pole like there. So they have the pair and they have the pair. Similarly, for this one, we need to express our 0. Probably the 0 is at that point. So how many poles and the zeros? We have find 3 poles and the 3 zeros. And this is of course an all pass filter, because it given the condition that if the pole location at any value b, the 0 location is at 1 by b, or vice versa. Okay, so that is the condition. Now this is how you can design your all pass filter. Okay, before going to the explanation how this shows the magnitude 1 for this one, okay, let me introduce our online platform by which you can we can observe our all pass filter. Okay, so first of all, you will find this section. Let me extend a little bit more. Yeah, you'll find that this is the all pass pole. So this is all pass pole. So from there you can find that. So let me design it. So at this moment we have the blank filter. We don't have the pole and 0. So here is all pass pole. This is poles and the zeros all together. So let me take it somewhere else, and you can see that that is the magnitude response and the phase response. Okay. Just a minute to restore the things again. Okay, we are restoring the web page. Okay. So we can cancel it out. Just a moment. Facing some problem or issues there. Just a moment. Okay, so here is the all pass pole. We just introduced that here, and as you can find here, this is the place where you can show the magnitude response. So at this moment I have only activated the magnitude, and if I activate the phase, you'll find the phase here. So we can deactivate the magnitude as well, just to see the phase response of that. Only the phase response is there. Okay, if we think about the magnitude response, what is the magnitude response? Of course, that is 1 for all the frequency component. And what about the phase response? You'll see that. Okay, so maybe it might have taken this. If we change the pole locations, you can see these are the complex poles. We have 2 poles and the 2 zeros, by which you can change. Please consider the phase response. Of course, that is a nonlinear phase response. If those are the real one, so we are making the real poles. There are the real poles and the zeros. As you can see that when the pole is very close to the unit circle, the 0 is also very close to the unit circle. And yesterday we have shown the hypothetical example, and this is exactly the same. So you can design any sort of the phase response with this kind of pole. Definitely, you can choose another couple of the pole locations. to make the things more difficult. Okay, so if you can consider how you can change the things, okay, control the things, maybe you need a number of couples of the poles and the zeros. So anywhere, everywhere, you can put a control over the phase of this. So the phase response can be shown in different manner. So that is the thing. You can play with this website for more understanding of the all pass filter, as well as other filters, as we have mentioned earlier. Okay. So this is a proof just for the all pass filter, how this magnitude is equals to 1. So you can go through this article and you will find it very simple. Proof is there. So previously it was like z to the power -1, z to the power -1. So it is mentioning like this, and this is as well the same one. So since this part is only carrying the phase, this is also carrying the phase. So we can neglect this part, and we can find that at the end, we can find that this is, if we took that this is a B, in that case, this is B over B star over B, where B star is the conjugate of the B. And since the conjugate of that, mention the value, they will cancel each other, and we have the value 1 for any value of the omega. So we can prove that for all pass filter, the magnitude is always 1. However, we have actually started with that notion that the magnitude is 1 for the all pass filter. How we have done that? So we have started with this. Let's say we have a all pass filter with the Z, and then we are multiplying with all pass filters, the inverse filter of that. So of course, it will give the 1. The magnitude will be definitely 1 for all the frequency. So that's why it's not very important to show it here as well. What would be the magnitude for the all pass filter? What is the use of all pass filter? By this time, you have the clear idea on the purpose of using the all pass filter. The main purpose of the all pass filter to control the delay of different frequency components. So make the phase response linear, or in other sense, the group delay make constant. So in many literature, people are telling that the delay equalization is the main purpose of the all pass filter. However, you already know that what does it mean and how you can implement the all pass filter. This is an example. I have taken this from online source. Probably this is very significant for our practical users, just to understand the process. First of all, let's say this is the pole 0 diagram, where we have 8 poles and 8 zeros. Of course, they are at the same place. Okay, so that is how you can show how many poles are there. Let's say if I have 10 poles at the center, or 12 poles at the center, I should write like this. So I have 12 poles at the center. So I have 8 poles are there. Of course, they are complex conjugate. That's why there would be 8 poles there. And due to these 8 poles, there should be 8 zeros. And due to these 8 poles, we should have 8 zeros. So that is very simple. And this is the equation for the all pass filter. Now, I believe that is very easy for understanding how the all pass filter works. And this is the phase response of this all pass filter, which is unfolded version. This is unfolded version, and this is the folded version. So after showing this unfolded version, this is the phase response, how they looks like. Okay, this is. Of course, this is a nonlinear phase response. No question about this. Don't confuse with these x-axis values. You can take it like this is pi by 2, and this 3 is equals to pi. Just let that. This is pi by 2, and this is pi. It means that, and this is 0. This 0 means you are there. This is 0, omega equals to 0. This is omega equals to pi by 2, and this is equals to pi. So this is a full cycle. So this is the full cycle, and we are showing the full cycle here. They are just normalizing the things for their literature. Okay, so don't just forget about this. This is a pi by 2, and this is pi, and this is 0. Okay, now how you can find the group delay of these all-pass filter? Very simple. What you need to do, you need to do minus d omega, the phase d phi omega divided by d omega, and that is the group delay, and that can be mentioned as tau, and that is nothing but the rate of change, negative rate of change. So whenever it is sharply falling down, that means it will sharply raised to some value. So what we are doing, this is just the rate of change of this diagram, and we can find that at the location of pi by 2, the value is almost 300. This is very significant. So the delay, this is a group delay plot at the location of at the frequency pi by 2, the delay is 300. For lower frequency or for the higher frequency, let's say at this moment, let's say this is pi by 4. At pi by 4, what is the delay? The delay is 0. That means the input signal reached to the output without any delay. Similarly, for the higher frequency, they will also reach to the output with the same time duration. There is no delay. But for the frequency of pi by 2, it makes a huge delay, and that is a 300 sample. And now what will happen if we put a signal xn to this kind of filter and we try to find the value of yn, how they looks like? Okay, so this is an example. We are giving our input and we want to see our output, where this is our all-pass filter. We have already discussed about. So this is our input xn. This is our xn. Try to see that this portion, the high frequency portion, been represented by pi by 2, and this low frequency portion is represented by pi by 8. Where is that? Those places, as I have already mentioned, that this is pi by 2, and let's say pi by 8 is there. Pi by 8 is there. Of course, pi by 8 is less than pi by 2. In case of pi by 8 frequency, there is no delay. So that means this will remain at the same location. They will remain at the same location. On the other case, this high frequency component, like pi by 2, that will be delayed for 300 sample. So this point will be shifted at 300 sample. This point means this 0th position is now shifted at 300 sample. And of course, the other positions will be shifted. The last position may be shifted like this. Okay, of course, since this is not a perfect convolution in the practice, so there might be some tail like this due to the mathematical error. But we can get the idea. The low frequency component, according to the group delay, that will remain at the same place. The high frequency component, they are shifted. All the frequency component, they are shifted to the right for 300 sample. And that is the practical applications of the all-pass filter. Now the thing is that where we should use this kind of filter, let's say your IIR type filter, let's say HZ, this is IIR type filter. In that case, the group delay is just an opposite of that. So they have this kind of scenario. Let's say they have this kind of scenario, the group delay, where the low frequency component have 300 sample delay and the delayed, and the high frequency pi by 2 is making no delay. So what will happen for this case? The low frequency component have the delay, so the low frequency component will shifted for 300 samples, and the high frequency component will remain at the same position. So let me draw that. If this part will be shifted, so let's say it start at 150, so it actually start with 150 plus 300, so 450, let's say, that is the starting point of the low frequency component and ended with some value. So this is 450. What about the high frequency component? Since we have already mentioned that there is no such kind of delay, so that means they will remain at the same place. So that has been done by an IIR type filter. IIR type filter. And definitely that makes a problem, isn't it? It makes a problem because that was our initial signal, but now we have some delay between the high frequency component and the low frequency. Now what we can do, this signal should be passed through by this kind of all pass filter, where the high frequency component is now delayed for 300 samples and the low frequency component will not be delayed for any samples. So what will happen, this high frequency component now, so let's say this is our 300 samples. So now this high frequency component will come over there, which is equivalent to our original signal. You can retrieve your original signal back. Is it clear to you? Is it okay to you?
Yes, sir.
Okay, so thank you. So that is the notion of using the IIR filter and the the all pass filter for the practical reasons. Okay. Now we need to move on. So this is the end of the basic filter design. Now we need to move to the discrete time Fourier transform. The discrete time Fourier transform. Sorry, this is discrete Fourier transform. Discrete Fourier transform. We have continuous time Fourier transform. In that case, the input is xt, and we got our x omega after doing the Fourier transform. Whenever we are talking about discrete time Fourier transform, the input is xn and we have the output x omega. So what about this x omega? This is a continuous one, continuous spectrum, because for all the values of omega, we can get a value. So that's why this is an analog representation. And now if we discretize this x omega, then this is called discrete Fourier transform. Discrete time Fourier transform. Here discrete time represent this discrete time signal. Discrete Fourier transform represent the Fourier transform is now discretized. What was your Fourier transform previously? If we look at this diagram, the diagram I have already mentioned here, if you can look up to 0 to pi, what we have learned previously, in the negative portion, we have the same sort of signal, isn't it? So we can extend up to minus pi, and let me draw it like this. Probably I can draw try to do it almost equal things over there. Okay, maybe like that. So you have this, and now what we have done, we can extend from minus pi to plus pi. Now we are considering from 0 to twice pi, and in case of x omega, this value is continuous, because for all the values of omega, let me choose another color, for all the values of omega, you are getting the value for different value of omega. However, this is continuous. Now, in case of computer, can you store all the value? Is that practical? The answer is no. This is not practical to store an analog sample or analog value. This is not possible because you can't take all the value. So then what is the strategy? The strategy is we need to sample it out. The omega is now sample it out, and we can store some value from this x omega that is a subset of this and can be represented xk. Now we are putting this is xk, where k is a subset of omega, and it can be represented as the k is definitely is equals to from 0 to n minus 1. The values are there, and where we have 0, 1, 2, and so on up to n minus 1. So that is the concept of the discrete Fourier transform. We are discretizing the discrete time Fourier transform. Discrete time Fourier transform, basically known as Fourier transform. Fourier transform, they are the same. Now Fourier transform is now discretized. Which one is the Fourier transform? This continuous value is the Fourier transform. Now whenever you discretize it, that is known as discrete Fourier transform. The concept is very simple. Why we should go for the discrete Fourier transform? Because the computer can't store all the value. So that's why we need the discretization of the value. Okay. So for this kind of process or algorithm, I'm talking about discrete Fourier transform, the xn should have capital N number of samples. So altogether capital N number of samples from 0 to n minus 1. Similarly, in the frequency domain, previously it was x omega. Now this is xk. What is xk? That is a different range of k. So that means x0, x1, x2, x3, and up to xn minus 1. So how many samples we have? We have capital N number of samples, and we choose those n number of samples from the spectrum of x omega. So how many samples we should choose? We should choose all together again capital N number of samples. So in the time domain, we have n number of samples. Let's say that is 20. In the frequency domain, we will divide our whole frequency spectrum. Frequency spectrum means from 0 to twice pi with a number of capital N, which is, for example, this is 20. That is a concept of the discrete Fourier transform. Now, if we think about what is the distance between these two, so from 0th sample and the first sample, what is the distance? Of course, the total distance is twice pi, and how many samples we are segregated from 0 to twice pi is capital N. So that is the jump of the frequency. At this level, that is 0. At this level, that means at this level, what is the frequency? That is twice pi divided by n in the scale of omega. At second point, that means at this point, what is the value? This is twice pi divided by n multiplied with 2. At third point, when k is equals to 3, what is the frequency value? This is twice pi by n. that is the unit of jump, and then multiplied with 3. That is the frequency at the moment of k is equals to 3. If I'm ask you that at omega equals to pi, what is the frequency at omega equals to pi? What is the actual frequency? At omega equals to pi, because we know that our spectrum is from minus pi to plus pi. So what is the actual frequency at the location of pi? This is in the scale of omega. Any of you?
0.5.
0.5 what? Actual frequency. What is the
Relative
actual frequency? Sorry?
0.5 is a relative frequency.
That means you are talking about f by 2. Is that?
Yes.
Okay. So it can be mentioned as definitely any point is related to omega is equals to twice pi f, small f. I'm talking about what is the actual frequency at omega equals to pi. So that means this is equals to pi. The omega equals to pi at that moment. So what is f? Twice pi. F is equals to f by fs is equals to pi. From there, we can find what is the actual frequency means f. F is equals to the pi will cancel each other. That is fs divided by 2. That is the actual frequency at the location of pi. This is very important. So what is your sampling frequency? You must know about the sampling frequency. Whenever you know the sampling frequency, you know that what is the frequency at the location of omega is equals to pi. Okay, similarly, for omega is equals to twice pi, what is the actual frequency? Of course, the actual frequency is fs. Okay, the actual frequency is fs. That is how we need to understand this full spectrum very, very clearly. This full spectrum very clearly. I have mentioned it again that at 0 means at k is equals to 0. What is the value of omega? This is twice pi small f. This is small f. This is 0. Of course, that is the zeroth value. However, we can find it like this. The omega, we have twice pi divided by n. That is the jump between these 2 points multiplied with 0 because k is equals to 0. So omega can be represented by twice pi n into k. So that is the relation between omega and the k value. For k is equals to 1, it will be omega is equals to twice pi by n into 1. So what is the frequency? The frequency is twice pi divided by n. What is the actual frequency? What is the actual frequency? Twice pi by n. What is the actual frequency? Let's say n is equals to 10. So that is equals to twice pi divided by 10. So that is equals to pi divided by 5. What is pi? We have already mentioned that this pi is fs divided by 2 divided by 5. So we can find fs divided by 10 is the actual frequency at the location of k is equals to 1. That is how you can find each and every frequency component of all the points for k is equals to 0, 1, 2, 3, 4, and so on and so forth. Okay. I have already mentioned here that the distance between 2 points is twice pi by n. Of course, that is true. For the first 0th point multiplied with 0, for the first point multiplied with 1. For the second point, it's multiplied with 2. So in general, what we can write this is, of course, you can understand that this number is a set of is a subset of omega, because omega is a continuous one. Omega is continuous from 0 to twice pi, all the values, but twice pi by n into k, where k is the value up to n minus 1. So these frequencies are the discrete. Of course, they are discrete. You can target this frequency, you can target this frequency, you can target this frequency and this frequency, so on. You can't target all the frequency. You can't target all the frequency. You can target almost all the frequencies. In Cartesian plane, you can represent the whole things. This is not very important, just to show that in the circular domain, that means whenever we are talking about the z plotting, so we have omega equals to 0 here, and omega is equals to pi, and this is omega is equals to twice pi. So this whole circle can be divided in n section. Okay, the same thing we have represented in the earlier page. How we can define those things in the by mathematical equation? What is, if I recall, what is the Fourier transform? How to define the Fourier transform of your xn? So we do the Fourier transform. X omega is equals to n is from 0 to n minus 1, because we have n minus n number of sample. We have xn. Okay, let me write it in this way. Previously, we thought that the xn it can be infinite as well. So x omega is equals to n is equals to from minus infinity to plus infinity. We have xn and e to the power minus j omega n. I believe you can recall this equation. Now for the discrete Fourier transform, what we are doing, xk. Now this function is also this notation is also a function of k, is equals to how many samples you have in xn in the time domain. That is n equals to 0 to n minus 1. We have already mentioned that. Okay, we'll take the samples from n equals to 0 to n minus 1. So that is our xn, and e to the power minus j. Now what is omega? We have already defined that the omega can be represented twice pi by n into k, and that is how omega is now omega is replaced with the value of k, because twice pi by n, this is a constant for a particular case, and the k is only the variable. So that's why omega can be replaced as twice pi by n into k, and this n will remain the same, and that is the discrete Fourier transform. Discrete Fourier transform. So I believe you understand. We have maybe the larger version. So we have write the same equation here. If you can recall, this is very important for everyone. This portion represent omega, and this n. What is the significance of this n? This n shows that if you can go back to the basic of the Fourier transform, what we have done, we have our xn. Let's say this is our xn. What is the first step? We actually sample it out. Okay, let me give the x-axis as well. Okay, we sample it out. First of all, we sample those things out. We are taking those samples. So this is our xn whenever we are taking the samples. And let's say e to the power minus j omega n, where omega is omega 1 for a particular frequency. What we have done for the cos part, that means for the real part, what we have done for the real part, we took a cos signal. We took a cos signal and sample it with the same sampling frequency, fs. We sample the xt with fs and we found xn. Similarly, we have this signal e to the power minus j omega. That is the signal omega 1. And then this n means that we are sampling the signal with the same sampling frequency. With the same sampling frequency means they are in the same time scale. They are in the same time scale. So you need to understand the physical phenomena of this n. This is very important. What does it mean by this n? Now, this is the first step. What is the second step? You need to multiply all the points. You need to multiply each and every points together. You are multiplying those values. And after that, what we'll do, you need to sum up. You need to make a summation for how many samples? From n equals to 0 to n minus 1. Because as we already mentioned that, here we have the 0th sample, 1, 2, 3, 4, 5, 6, 7, and 8. Let's say we have 9 samples. We have 9 samples. We have total 9 samples, 0 to 8. So how many samples you have? So exactly in this course, we are taking these 9 samples starting from the 0, and we are multiplying these two equations together, and all together we'll find this equation. So I believe that you can understand the portion of what is xn, of course, and from 0 to n minus 1 of the xn. Similarly, e to the power minus j twice pi by n into k, that actually represent the frequency, and this n represent the same sampling frequency, and these n values. That is a function of this n values. So how many samples you can get it from this the cos signal and the sine signal? How many samples? The same number of samples you are taking from your xn. Okay. And now what the people are doing, they are making the things little bit concise. And as you can understand that this portion is constant for a particular case. Whenever the n is a value, you need to choose that value. So this is typically a constant value, and this can be mentioned as w n to the power minus 1. That is, so the wn, this is wn, this subscript n represent this value of n, and kn is represent this value kn. So we can find that this wn is equals to e to the power minus j twice pi by n. So if I put a w4, that means that we have how many samples you are taking? You are taking 4 samples from xn, and you have the k value. K is also from 0 to 3, and n is also from 0 to 3. That what does it mean by w4? So you have total 4 samples. Okay. Now, if we talk about the inverse discrete Fourier transform, similar to the inverse Fourier transform, we have xn. How many samples you have? It's very simple, from 0 to n minus 1. Then e to the power, previously it was a minus, now it is plus e to the power j twice pi by n kn. I believe each and every part is known to you. And we need to make an average of this. That's why this is 1 over n. So that is the inverse discrete Fourier transform. So we can write it very easily that this is our discrete Fourier transform, and this is the inverse discrete Fourier transform. Be careful that this wn is equals to e to the power minus j twice pi divided by n. And Wn minus 1 is equals to e to the power j twice pi divided by n. Okay. Now there is a very significant observation is that try to understand that what is the pattern of xk? Is that a periodic or aperiodic signal? From our experience, what we can see that in the frequency domain, from 0 to minus pi to plus pi, and after that it will definitely repeat again and again. It will repeat again and again, because that is a function of e to the power minus j omega n. That is a function of omega, and this omega is a periodic function. This omega is a periodic function which contains the period from 0 to twice pi is the period of the omega. So that's why this function is a periodic function. You have the first lobe, now you have the second lobe, and it will move to the negative direction and the positive direction as well. That's why whenever you are multiplying any function with e to the power minus j omega n, then it moves to the periodic function. Since we already know that the k is nothing but we have the relation between k and omega. Omega is equals to twice pi divided by n into k. If we can extend the value of k, of course we can find the frequency component. Since this omega is a periodic signal, for any value of the omega we can find this frequency. So it is very I would say easy to understand that this xk is also periodic, because wn, or in the other sense e to the power minus j twice pi by n, they are twice pi by n, they are periodic. They are periodic. After twice pi you are getting the same value. After twice pi you are getting the same value. So this is a periodic one. Similarly, if we look at to this, now this xn is also a function of e to the power j omega. Omega is equals to, I would like to say, twice pi by n into k. So since this is also a function of omega, now this xn is also a periodic signal. What I try to make you understand that whenever we start with xn, that was a aperiodic signal. Let's say this. Of course, they are sampled. You understand that. And whenever we pass it through the discrete Fourier transform process, we get xk, which is a periodic. This is a periodic signal. Now, whenever we are dealing with inverse Fourier transform, inverse discrete Fourier transform, inverse discrete Fourier transform, at that moment we found xn back. However, that is a periodic signal. From the graphical perspective, we can show that this is the phenomenon. So we start with this kind of xn. We have the samples like this. How many samples we have? 0, 1, 2, 3. We have 4 samples. And after doing the Fourier transform, discrete Fourier transform, we got xk, which is a period of 1. Whenever we come back to our xn original signal, we found that that is converted to a periodic signal. We are doing inverse discrete Fourier transform. And now the signal looks like this. However, we need to focus to the value from 0 to n minus 1. We do not need to check any other value. Otherwise, that will be problematic for us. This is true both for xk. Xk is a periodic signal. What is our range of view? Range of view is from 0 to twice pi. Xn, after doing the inverse Fourier transform, it is also periodic. What is our range of view? Is 0 to n minus 1. I I'd like to mention this again. This is not true. From 0 to twice pi is the range of x omega. Whenever we are talking about xk, the range is from 0 to n minus 1. That is the range of xk, because the n minus 1 point actually represent twice pi, 0 represent this 0. Okay, so that is the starting or the initial point of the discrete Fourier transform. I believe that is enough for today's lecture. So in the next day, we'll continue this discrete Fourier transform. Maybe we need 1 or 2 classes for this. And after that, we have first Fourier transform. That is an algorithm. It will take 1 class more. So I believe that within 3 classes, we can wrap up our syllabus. And after that, we can make our review classes if we have any question on the syllabus. Okay. So at this moment, do you have any question?
Sir, generally we are concerned with frequencies from
I
0 to pi.
can't hear you.
Sir, generally we are concerned with frequencies from 0 to pi.
Yeah.
Why is in the case of DFT we are concerned with 0 to 2 pi?
Okay. The thing is very good question. For the filter design, let me give you this example. Whenever we start the filter design, so if you can recall, we have mentioned this. Let's say this is omega c, this is minus omega c. This is a typical low pass filter. This is pi and this is minus pi. So whenever we are talking about this is a transfer function of a low pass filter. So we always need to take this negative frequency component, the negative frequency component, as well as the positive frequency component, due to the mathematical concept. What is the negative frequency? Whenever we are just rotating in opposite direction. So if your vector is rotating anti-clockwise, that is a positive frequency. When it is rotating in the clockwise direction, that is negative frequency. So in mathematics, whenever we are talking about the Euler's identity, whenever we are taking a cos function, moving to the Euler's identity, changing from the Euler's identity, whenever we are talking about the exponential term, we have e to the power j theta and e to the power minus j theta. What does it mean, j theta minus j theta? They actually means 2 frequencies. One is positive frequency and another one is negative frequency. And that is why we are presenting our transfer function like this. And whenever you need to do the inverse Fourier transform, what we are doing the integration from minus pi to plus pi and taking the value. Okay, so taking the value. So what is the value of x omega? And then we are dealing with d omega, and we are making the average of that, and we found the value of xn. Okay, or you can say xt or xn. Okay, so we got it from the integration from minus pi to plus pi, not necessarily from the 0 to pi. That is not enough. Okay, if you make an argument that okay, I can do it from 0 to pi as well, yes, we can also do that, because we know that this portion is a replica of this portion. That is how you can do that. But straightforward, we need the integration part from minus pi to plus pi. Similarly, what we can do for the same example, we can do the followings. Since they are repeating, what we can do in the next semester, we'll find it more clearly that let me choose another color. This is 0, this is omega c, let's say this is a pi, and let's say this is twice pi, and this is a minus omega c, this is a minus pi. Now what you can do, you can take the samples or the integration from 0 to twice pi for this area, and that is equivalent to that one. They are the same. Now, by not considering the negative part, we can also consider the positive part as well, from 0 to twice pi, that which is equivalent to considering the part from minus pi to plus pi. And that's why this is justified, that we can take the spectrum from 0 to twice pi. There is no problem. Okay.
Sir, understood.
Okay. So thank you very much for your question, and I believe that it will be helpful for understanding. Okay. Still, you need to think more about the problem and the issues. If you have any doubt, just in the class time, you can raise the question so that we can discuss and make it clear for our class. Yeah. Thank you for your participation. Thank you.